Imagine for a moment a world that is, against all we know of astronomy and geology, perfectly and utterly flat. An unblemished plain stretching out before you, uninterrupted to a horizon that is impossibly distant. And you find yourself standing upon it, on the darkest, most moonless and clearest night imaginable, a night entirely devoid of any artificial light pollution whatsoever. Not a single distant city glow, not a stray car headlight to interfere. In conditions as pristine as these, our visual system possesses a sensitivity so truly remarkable that you would theoretically be capable of discerning the faint ephemeral flicker of a single match being struck and ignited, a tiny pinprick of light from an astonishing distance of approximately 48 kilometers. Now, just take a moment, if you will, to truly, deeply and viscerally contemplate the profound implications of such a feat of perception. 48 kilometers. Imagine that distance. It's the length of a full marathon, and then some, stretching across a vast dark plain. The sheer magnitude of this distance, paired with the minuscule nature of the light source, a single, fleeting flame, evokes an almost overwhelming sense of wonder, a recognition of the miraculous, almost magical capabilities inherent within our own biological makeup, within the intricate machinery of the human eye, and the powerful processing capabilities of the brain. It speaks to a sensitivity that borders on the quantum, an ability to reach out across vast emptiness and register the faintest whisper of energy. This astonishing capacity for light detection is not merely the stuff of anecdotes, poetic imaginings, or theoretical conjecture. It has been rigorously and meticulously investigated through decades of dedicated, painstaking scientific inquiry. As far back as the pivotal year of 1941, the eminent vision specialist Selig Hecht and his distinguished colleagues at Columbia University conducted what remains to this very day a benchmark and highly reliable measurement for the absolute threshold of human vision. Their pioneering experiments were designed with an almost obsessive attention to detail, seeking to determine the irreducible minimum number of photons, those fundamental indivisible packets of light energy, the smallest possible units of light, that must impinge upon the retina of the human eye to elicit a conscious, undeniable sensation of visual perception. This was, in essence, a quest to find the absolute lower limit of our ability to sense the universe, to touch the very edge of what is perceptible. The experimental conditions for this groundbreaking research were meticulously crafted to be as ideal as possible, pushing the boundaries of human sensitivity to their absolute physiological limit. Participants in the study were given an extensive period of time, often spanning several hours, to fully adapt their eyes to conditions of complete and utter darkness. This prolonged period of dark adaptation is absolutely crucial, as it allows the photoreceptor cells in the retina, particularly the highly light-sensitive rod cells, to regenerate their light-sensitive pigments, primarily a molecule called rhodopsin, and reach their peak capacity for gathering even the faintest available light. During this time, the eye's sensitivity increases by a factor of up to 100,000. It's an incredible biological transformation, turning our eyes from daylight instruments into exquisite nighttime detectors. The stimulus itself was a brief, almost instantaneous flash of light, precisely calibrated to a specific blue-green wavelength of 510 nanometers. This particular spectral region is of paramount importance because it is the exact wavelength to which the human eye, specifically its rod photoreceptors, is most acutely and exquisitely sensitive, aligning perfectly with the peak absorption of rhodopsin. This makes it the most efficient wavelength for detecting minimal light. Furthermore, this carefully controlled light stimulus was directed with pinpoint accuracy towards the periphery of the retina, an area known to be densely populated with these highly light-sensitive rod cells, which, while not contributing to our perception of colour, are incredibly efficient in low-light conditions and possess a much higher density than the cone cells in the centre of our vision. Have you ever, perhaps during a night spent in quiet contemplation, gazing upwards at the vast star-strewn canvas of the night sky, noticed that you can sometimes perceive the faintest, most elusive and otherwise invisible stars more readily when you avert your direct gaze slightly, allowing their faint, distant light to fall upon your peripheral vision? Yet, paradoxically, when you attempt to fixate directly upon them, to bring them into the sharp focus of your central vision, they seem to vanish, dissolving into the impenetrable darkness, becoming utterly imperceptible. This commonly experienced perceptual phenomenon is a direct and elegant manifestation of the high concentration and heightened sensitivity of the rod cells in the retinal periphery. These cells are exquisitely adept at detecting incredibly dim light sources, even single photons that are foveal vision, the small central pit of the retina dominated by cone cells and responsible for sharp, detailed colour vision in bright light, might entirely miss due to its lower sensitivity and darkness. The fovea, while providing high acuity, has very few rods. It's a beautiful, direct experience of the specialised architecture of your own eyes. Through their diligent, meticulous and precise work, the scientist involved in Hecht's study discovered a truly astonishing and humbling fact. The perception of light, the very awareness of something being present in the visual field, could be triggered by the absorption of an extraordinarily small number of photons, a range as minuscule as 5 to 14 individual photons. This is an almost negligible, infinitesimally small quantity of light, a testament to the quantum nature of vision, representing the activation of merely 5 to 14 individual rod cells out of the staggering approximately 100 million such cells that populate each human retina. When this incredibly low, almost unbelievable threshold is met, when these few photons are successfully absorbed, a meticulously orchestrated and highly efficient cascade of biochemical and electrical signals is initiated within the photoreceptor cell. This cascade, involving a series of molecular events, culminates in a message being transmitted along the optic nerve to the brain, informing it with astonishing clarity and reliability that something, however faint, however subtle, has indeed been perceived. It's a direct link between the quantum world and our conscious awareness. And yet this is only one facet of our sensory world. Our senses are, without exaggeration, truly astounding, possessing an almost unfathomable acuity and an immense breadth of perception that allows us to engage with the intricate tapestry of the world in ways that are both profoundly subtle and breathtakingly grand. Let us for a moment delve into the remarkable and often overlooked capabilities of our auditory system, an intricate biological marvel of evolutionary engineering. With our ears, these exquisitely sophisticated organs nestled on the sides of our heads, designed to capture and interpret the subtle vibrations that permeate the air around us. We're not only capable of discerning the overwhelming, thunderous roar of a supersonic jet as it cleaves through the atmosphere with a deafening boom. This is a sound that embodies immense power, blistering speed, and the sheer force of human ingenuity pushing against the very limits of physics, a phenomenon where air molecules are violently compressed and expanded, creating shock waves that register as an almost painful assault on our eardrums. A sound so powerful it doesn't just enter our ears, it reverberates through one's entire being. A visceral experience of raw energy that can literally shake the ground beneath one's feet and vibrate through the very bones of the body, a testament to the sheer scale of energy involved. Yet, with these very same exquisitely sensitive organs capable of withstanding such acoustic extremes, we can also perceive the gentle, almost imperceptible and exquisitely quiet rhythmic tap of individual water droplets as they slowly, almost reluctantly fall from a faulty faucet in the profound stillness of a quiet room. This is a sound so soft, so delicate, so utterly devoid of overt power, that it might barely register on our conscious awareness during the cacophony and ceaseless clamour of the day, easily lost amidst the myriad other ambient noises. However, under the profound and enveloping cloak of deep night, when the world outside has hushed its ceaseless activities and one attempts to drift into the tranquil embrace of sleep, this seemingly innocuous sound, this tiny repetitive plink, can transform into a relentlessly maddening, singularly focused annoyance, its monotonous rhythm drilling into the mind with an almost hypnotic, irritating persistence. Each solitary drop, a tiny acoustic event, becomes magnified in the silence, its precise timing and pitch, a torment to an overactive mind seeking repose. This vast, almost incomprehensible dynamic range of our auditory system, extending from the deafening might of a jet engine to the whispered, almost ethereal annoyance of a dripping tap, stands as a profound testament to the intricate, complex, and extraordinarily adaptive engineering of our hearing apparatus. This biological masterpiece encompasses the delicate mechanics of the external ear, which funnels sound waves, the vibrating eardrum, which converts sound into mechanical motion, the tiny, perfectly articulated ossicles, the malleus, incus, and stapes, which amplify these vibrations, and the fluid-filled cochlea, a coiled, snail-shaped chamber lined with thousands of microscopic hair cells. These hair cells, exquisitely tuned to different frequencies, translate the mechanical vibrations into electrochemical signals, which are then transmitted along the auditory nerve to specialized processing centers in the brain, where these diverse inputs are integrated into a coherent and nuanced auditory experience. It allows us to interact with our acoustic environment with astonishing precision and awareness, distinguishing not just volume, but also pitch, timbre, and spatial origin. Our sense of touch, an equally miraculous and often undervalued facet of our sensory repertoire, offers a similarly expansive spectrum of experiences, ranging from the brutally tangible and impactful to the almost ethereal and fleeting, defying any easy attempt at categorization or simple description. It permits us to feel the distinct, often uncomfortable pressure, and the sharp, sometimes cutting edges of the handles of a heavy grocery bag, perhaps laden with 10 kilograms of provisions, the cumulative weight of which digs mercilessly and unyieldingly into the delicate flesh of our fingers. The strain is palpable, a dull ache radiating from the points of contact, the indentations visible in the skin, the very coarse fibres of the shopping bag material, making their presence known through direct physical contact and deformation of the epidermal layers. This is a sensation of sustained, localized pressure, often accompanied by a dull ache or even a sharp pain if the weight is excessive or prolonged. And yet, almost simultaneously, or perhaps just a fleeting moment later, this identical, highly sensitive somatosensory system enables us to register the incredibly delicate, almost weightless, feather-light brush of a mosquito's minuscule legs as it gingerly and tentatively alights upon our skin, a creature weighing barely 2 milligrams, its presence almost negligible in terms of mass, its contact barely disturbing the air molecules, yet its intent, however, potentially quite impactful, foreshadowing an itch or a bite. The profound contrast between these two disparate tactile sensations, the crushing, insistent and often painful weight of a heavy load, and the almost imperceptible, fleeting and gossamer-like contact of a minute insect, highlights the truly remarkable sensitivity, the vast dynamic range, and the exquisite discrimination capabilities of our somatosensory system. This system is not a monolithic entity, but rather a complex distributed network populated by an astonishing array of specialized receptors. These include Meissner corpuscles, which are adept at detecting light touch and changes in texture, Merkel cells, sensitive to sustained pressure and subtle shapes, Patinian corpuscles, which respond to rapid vibrations and deep pressure, and Ruffini endings, which detect skin stretch and sustained pressure. In addition, free nerve endings transmit sensations of pain, temperature, and crude touch. Each of these receptor types is meticulously tuned to detect different types of mechanical stimuli, from deep bone-pressing pressure to the most subtle, barely there vibrations that travel across our skin. These diverse receptors, distributed unevenly across our body, sending their specific signals through a complex network of peripheral nerves and ascending spinal cord pathways, ultimately reach specialized processing areas of the brain, such as the somatosensory cortex. Here, these diverse inputs are integrated, interpreted, and synthesized into a coherent, nuanced, and spatially accurate tactile experience, allowing us to interact with our physical environment with astonishing precision and awareness, distinguishing not just what we touch, but how, where, and with what force. Indeed, among the entire pantheon of our senses, hearing, touch, taste, smell, and vision undeniably occupies a singularly prominent, almost preeminent position in terms of the sheer volume and complexity of information it delivers to our conscious mind. It is through the intricate and highly complex machinery of our visual system that we process the overwhelming majority of incoming sensory information, meticulously constructing our internal, subjective model of the external world. Existing estimates, based on extensive research in neurobiology, cognitive science, and computational neuroscience, suggest that the human visual system processes data at an astonishing, almost dizzying rate, handling approximately 10 million bits, or units, of information every single second. To put this into perspective, consider the amount of data in a high-definition video stream. Our eyes and brain are doing something vastly more complex and dynamic. This immense bandwidth, this extraordinary capacity for rapid and sophisticated data processing, is what allows for the intricate, detailed, and dynamically updated construction of our perceived world, enabling us to navigate complex environments with remarkable agility, interact with objects and other beings with astonishing precision, and comprehend our surroundings with profound detail, speed, and accuracy. The brain's visual cortex, a vast and complex network of interconnected areas, works tirelessly to interpret these signals, identifying patterns, recognizing objects, and constructing a coherent, stable visual reality. Without the profound and invaluable gift of sight, it is highly probable, almost certain, that astronomy as a rigorous scientific discipline devoted to the study of celestial objects and phenomena would never have emerged in its current form. The vast, silent, and endlessly enigmatic expanse of the cosmos, with its distant shimmering glimmer of countless stars, the faint swirling nebulae, and the majestic distant galaxies, all of which are revealed to us primarily through the photons they emit, would remain forever hidden, an unreadable, unopened book in the eternal night sky, its profound secrets locked away from human curiosity and intellectual exploration. Our understanding of the universe would be immeasurably poorer, limited to what we could infer from gravitational effects or other non-visual cues. However, a fundamental and deeply unsettling question, one that I frequently raise and explore in these extended contemplations, persists at the very core of our understanding of perception and reality. Do we truly, in any comprehensive or exhaustive sense, know what lies beyond the inherent confines and the profound limitations of our biological senses? Do we in fact perceive reality as it genuinely, objectively is, in its unmediated, unfiltered, and complete totality? The unequivocal answer, I propose, is a resounding and unambiguous no. Moreover, and this is not a mere metaphorical flourish or an poetic exaggeration, but a statement of profound scientific and philosophical truth, we are, in a deeply unsettling and perhaps humbling sense, infinitely distant from perceiving reality in its complete, unvarnished entirety. Our sensory apparatus acts as a filter, allowing in only a tiny fraction of the information that bombards us. As Max Planck, one of the most brilliant and foundational figures of quantum physics, a man who peered into the very heart of the universe, so eloquently and presciently stated, modern physics produces a peculiar impression precisely because of the age-old truth that there exists a reality which we're not in a position to perceive by our sensory organs. He further elaborated on this profound insight, explaining that there are certain tasks, certain challenges, and certain conflicts, both scientific and existential, in which this unperceivable reality plays a far, far more significant and pivotal role for us than all the accumulated treasures and readily accessible data of the entire sensory world combined. This profound notion compels us to fundamentally reconsider the very nature of our existence within the grand, bewildering, and often hidden cosmos. It suggests that our everyday experience, while rich, complex, and vital for survival, is merely a thin, shimmering veneer, a carefully constructed illusion over an infinitely deeper, more expansive and profoundly mysterious truth. What we experience is not the territory, but a highly simplified map. The intricate boundaries and the ultimate capabilities of human knowledge are the central defining focus of gnoseology, a branch of philosophy also frequently referred to as epistemology. This field is concerned with the theory of knowledge itself, its origins, nature, methods, and limits. In simpler, more accessible terms, Gnoseology meticulously examines the complex and multifaceted process of knowing, delving into the intricate and dynamic relationship between the one who knows, the conscious, subjective observer, the individual experiencer, with all their inherent biases and biological constraints, and that which is known, the objective, external reality, the phenomenon, the fact, or the concept being apprehended. This demanding and intellectually rigorous field delves deeply into foundational and often perplexing questions such as, what precisely constitutes knowledge? Is it merely justified true belief or something more? How is knowledge acquired, processed, stored, and validated? What are its inherent limits, its fundamental boundaries, and how can we ascertain its ultimate validity and reliability in the face of our subjective experiences? This field forces us to directly confront the inherent filters, the interpretative frameworks, and the constructive processes that our minds inevitably impose upon the raw, unadulterated data supplied by our various senses. It strongly suggests that what we subjectively experience as reality is not a direct, unmediated, or perfectly objective apprehension of the external world, but rather a sophisticated, highly personalized, and constantly updated construction, a model painstakingly built by our brains based on limited, often incomplete, and sometimes biased sensory input. This cognitive construct is profoundly shaped by our evolutionary history, our individual experiences, our cultural context, and the very specific, intricate architecture of our neural networks. It is a reality built for us, not necessarily as it is. Recall, if you will, Plato's timeless and profoundly influential allegory of the cave, a philosophical narrative that continues to resonate with startling relevance and uncanny prescience, even in our most technologically advanced and information-saturated age. In this allegorical tale, a group of prisoners is depicted, having been confined from birth within the deep, shadowy recesses of a subterranean cavern. Their necks and legs are shackled in such an unforgiving, rigid and inescapable manner that they are perpetually compelled to face only the rough, unyielding wall directly before them. They are utterly unable to move their bodies, unable to turn their heads, unable to interact with each other, their entire existence, their entire perceived reality, defined by this singular, unchangeable and brutally limited perspective. Behind them, a roaring fire burns, casting its flickering, dancing light, and between this fire and the unfortunate prisoners, unseen by them due to their constraints, puppeteers manipulate various objects, figures of people, animals, and other artifacts, casting their distorted, elongated, and dancing shadows upon the very wall that the prisoners are forced to confront. For these unfortunate souls, who have known no other experience, no other reality, these flickering two-dimensional shadows, these mere spectral projections of unseen objects, constitute their entire, undisputed and unchallenged world. They perceive a reality that is confined, small, flat, and entirely monochromatic, composed solely of fleeting shades, indistinct outlines, and the transient interplay of light and dark. They may even name these shadows, discuss their movements, and believe they are experts on the nature of reality. The most dreadful and truly horrifying aspect of their predicament is not merely their severely limited and distorted perception, not just their physical confinement, but their profound, utter, and tragic inability to even conceive, to even imagine that the true world, the world of real, three-dimensional objects, of vibrant living colours, of boundless depth, of texture and complex interactions, is infinitely, incomprehensibly, and fundamentally different from the ephemeral, illusory dance of shadows on their cave wall. They tragically mistake the appearance, the mere superficial projection, for the true essence, the original, unvarnished, and infinitely richer reality. They are trapped not just by chains, but by their own unquestioned assumptions about the nature of existence. Are we, in our own daily lives, in our own conscious experiences, not perhaps too eerily similar to those ancient shackled prisoners? Even if we were to momentarily set aside the profound and often abstract depths of philosophy, with its intricate arguments and nuanced distinctions, and instead consider this question purely from a rigorous, objective, and physical perspective, do there exist infinities, dimensions, spectra, forms of energy, types of information that remain entirely hidden, utterly concealed from our direct perception, much like the real objects were hidden from the prisoners? The answer, unequivocally and with profound implications, is yes. We're about to embark on an intellectual journey to uncover, or at least glimpse, some of these hidden dimensions, these unperceived realms of reality that surround us at every single moment, constantly bombarding us with information, influencing our world in ways we're only just beginning to comprehend, much like the sun outside the cave influenced the shadows within. Let us commence our extended exploration by taking light as our initial point of focus, considering it not as an abstract concept, a mere philosophical construct, but as a tangible, physical phenomenon, a fundamental aspect of the universe that our sense of vision is ostensibly designed, through millions of years of evolutionary adaptation, to perceive and interpret. We will then engage in a crucial comparative exercise, meticulously juxtaposing this objective physical reality of light, its measurable properties, its fundamental nature, with the subjective sensation, the intricate, personalized, and often deceptive projection of reality that forms within the confines of our own minds. This entire extended exploration, this deep dive into the nature of perception and reality, is, in its very essence, an adaptation of the brilliant, profound, and truly illuminating insights of the American theoretical physicist and Nobel laureate, Frank Wilczek. More precisely, it draws heavily, almost exclusively, from the core ideas, and indeed, the very intellectual essence of a single, exceptionally profound chapter within his remarkable and highly acclaimed book, A Beautiful Question, Finding Nature's Deep Design. His entire monumental work, stretching across numerous pages and intricate arguments, is in itself a prolonged, deeply meditative and intellectually rigorous inquiry, meticulously designed to address a singular, overarching and profoundly beautiful question, one that he explicitly poses at the very outset of his book, directly challenging the reader to consider: does our world embody beautiful ideas? That is, can our world, in its deepest, most fundamental structure, in its underlying laws and symmetries, be considered a work of art, a masterpiece of cosmic design, imbued with an intrinsic aesthetic quality? It is to many quite an unexpected and perhaps even startling encounter to hear such poetic, aesthetic, and almost spiritual formulations from one of the greatest and most rigorous contemporary physicists, a man steeped in the logic of mathematics and the precision of experiment, yet possessing a deep appreciation for beauty. This juxtaposition of scientific rigor and aesthetic contemplation is a testament to his expansive intellect, his interdisciplinary approach, and his profound appreciation for the elegance and inherent beauty found in the fundamental laws of nature. The particular chapter that forms the central core of our current extended discussion, aptly titled The Doors of Perception, provides profoundly illuminating and often startling answers to a wide array of intriguing and frequently counterintuitive questions. It delves deeply into inquiries such as: are there in fact infinities of information and dimensions existing right before us, literally under our noses, constantly impacting our reality, that we simply do not perceive or are biologically incapable of perceiving with our natural senses? What, fundamentally and essentially, is colour? What are its physical underpinnings, its objective properties, and how does our brain construct this rich, subjective experience from mere wavelengths of light? And, in a truly astonishing and almost science-fictional revelation, how do some rare individuals, specifically certain women, experience colour vision not in the familiar three dimensions that most of us inhabit, but in an expanded, richer and more detailed four dimensions, perceiving hues and distinctions that are utterly invisible to the rest of humanity? These are but a few of the profound and often mind-bending revelations contained within the pages of this singular chapter. This specific chapter, while exceptionally rich and dense with complex ideas, is by no means the only one from Wilczek's extraordinary and expansive book that I would wish to discuss and explore in such extensive detail. Perhaps in the future, if I feel I can adequately and comprehensively convey the inherent beauty, the intellectual elegance, and the profound depth of the ideas presented, I may indeed choose to explore and elaborate upon other sections of his magnificent work, continuing this journey into the hidden facets of reality. Throughout the entirety of the book, one is constantly captivated and intellectually stimulated by the author's truly remarkable ability to synthesize disparate fragments of scientific knowledge, drawing from quantum mechanics, cosmology, particle physics, and more, patiently drawing from them, piece by painstaking piece, something coherent, deeply meaningful, and genuinely magnificent in its scope and implications, much like an artist constructing a masterpiece from individual strokes. Frank Wilczek posits a compelling argument that true modern physics, and indeed the entirety of our contemporary information-driven civilization as we know it, with its vast networks of communication, its digital marvels, and its deep understanding of energy, arguably began with the groundbreaking work of an individual who remains, to a significant extent, largely unknown to the general public today. This was a person without whose absolutely foundational and revolutionary discoveries, the very act of experiencing this extended monologue, transmitted wirelessly across vast distances and rendered on glowing screens, would be utterly, fundamentally, and unequivocally impossible. Albert Einstein himself, a figure synonymous with scientific genius, and a man whose portrait adorns countless classrooms, held a photograph of this individual prominently displayed on his office wall, a profound and deeply personal mark of respect and intellectual admiration, acknowledging a debt of gratitude. When asked, on one memorable occasion, if he believed he stood on the shoulders of the towering figure of Isaac Newton, whose laws of motion and universal gravitation had dominated physics for centuries, Einstein famously and humbly responded, "No, I stood on the shoulders of Maxwell." The individual in question, this intellectual giant whose profound influence permeates so much of modern life, even if his name is not on everyone's lips, is the brilliant British theoretical physicist James Clerk Maxwell. And Maxwell, to put it mildly, possessed an intense, almost obsessive fascination with all the intricate, perplexing, and often counterintuitive problems surrounding human perception and the fundamental nature of reality, constantly questioning what we truly perceive. In the 4th century BCE, a pivotal period in ancient Greece, when philosophy and what we now recognize as early forms of scientific inquiry were deeply intertwined and developed in an inseparable, symbiotic relationship, the Pythagorean school of thought formulated one of the earliest systematic theories of light and vision. This was a time when observation and reason were beginning to challenge mythical explanations. According to this particular view, a fascinating but ultimately incorrect emission theory of vision, visible rays were believed to emanate directly from the human eye itself, extending outward into the environment to literally feel or touch an object, thereby generating the sensation of sight. The eye was seen as an active projector rather than a passive receiver. This was a direct, active process on the part of the observer, a sort of visual palpation. Later, in his renowned and influential natural philosophical dialogue, Timaeus, the towering figure of Plato, further elaborated upon this concept, integrating it into his broader cosmology. He wrote, in a passage that beautifully illustrates the prevailing thought of his era and the struggle to understand the senses, that, of the organs, the gods first constructed the light-bearing eyes, and the gods made it so that the fire kindred to the daylight, which is within us, flows out purified through the eyes. This fire, this inner light, was thought to merge with the external light. When faced with the obvious and rather challenging question of why then, human beings perceive nothing at all in conditions of complete darkness, when there is no external daylight to meet the internal fire, various ingenious, albeit ultimately flawed explanations were devised to attempt to reconcile this emission theory with the observed reality. These explanations often involved the notion that the emitted fire from the eyes needed to interact with an external daylight fire, or that the darkness somehow impeded the outward flow of ocular rays, making vision impossible. The lack of external light was seen as a barrier to the emitted light's effectiveness. Today, thanks to centuries of rigorous scientific advancement, painstaking experimental verification, and meticulous observation, we possess a far more accurate, comprehensive, and nuanced understanding of the intricate mechanics of vision. We know definitively that our eyes do not in fact emit any rays whatsoever. They are not projectors of light. Instead, they function as exquisitely sophisticated and highly specialized receivers, passive yet incredibly complex organs, processing the visible light that originates from external sources, be it the sun, a lamp, or a glowing screen, and subsequently enters their intricate structures. It is crucial to reiterate, for the sake of absolute clarity and profound understanding, that light encompasses far, far more than merely what emanates from a simple incandescent lamp, the brilliant disk of the sun, or the distant shimmering points of stars. Light, in its most fundamental and all-encompassing sense, is, quite literally, everything that we perceive, everything that allows us to sense the world visually. You do not, for instance, perceive a ceramic mug as an intrinsic entity in itself. You do not directly apprehend its mugness. Rather, what you're actually perceiving are the countless photons of light that have originated from some light source, travelled through space, reflected off the mug's specific surface, carrying information about its colour, texture and shape, and subsequently entered the intricate, delicate structures of your eyes, ultimately landing upon the light-sensitive surface of your retina. This might not strike many as a particularly novel or revolutionary assertion, as it is taught in basic science classes, yet we rarely, if ever, pause to truly contemplate its profound implications and its fundamental challenge to our intuitive, unexamined understanding of reality, which often assumes we sense objects directly. But there is an even deeper, more astonishing layer of understanding, something that perhaps very few individuals throughout history have ever truly pondered or even conceived of with the clarity and rigour that Maxwell did. In the pivotal year of 1864, James Clerk Maxwell published a seminal and utterly revolutionary paper titled A Dynamical Theory of the Electromagnetic Field. Within this monumental and paradigm-shifting work, which stands as one of the greatest achievements in the history of science, one can find, for the very first time in human intellectual history, a set of 4 elegant and profoundly powerful equations that remain absolutely central, indispensable, and foundational to the entirety of physics today. These are, of course, Maxwell's equations. These elegant and profoundly powerful mathematical expressions fundamentally transformed our entire comprehension of the physical universe, uniting disparate phenomena into a single cohesive framework. Prior to Maxwell's groundbreaking work, while electricity and magnetism were recognized as distinct physical phenomena, each with its own observable effects, static electricity, magnetic attraction, they were largely understood as separate and independent forces, governed by their own unique sets of laws and investigated by different branches of science. It is now common knowledge, almost taken for granted, that an abundance of various fields, gravitational fields, electromagnetic fields, quantum fields, surrounds us, permeating all of space, many of them imperceptible to our direct senses. But before Maxwell, the very concept of a field as a fundamental form of matter, a pervasive medium through which energy and forces propagate, a continuous entity filling space, simply did not exist in its modern, coherent, and mathematically rigorous sense. Maxwell was the intellectual pioneer, the visionary who, through his equations, mathematically imbued the seemingly empty vacuum of space with these dynamic, energetic flows, these invisible currents of energy that, with profound elegance and astonishing precision, govern the very fabric of our physical world, from the smallest atomic interactions to the vastness of cosmic radiation. Furthermore, these same revolutionary equations provided humanity with an entirely new, unified, and infinitely more profound understanding of the very nature of light itself. They revealed, with stunning clarity, that what we subjectively perceive as light is but a minuscule, almost infinitesimally small fraction of a much vaster, infinitely more complex and largely hidden reality. Maxwell's equations not only described visible light, which had been studied for centuries, but with astonishing prescience, they predicted the existence of light, or more accurately electromagnetic radiation, that remains entirely beyond the scope of our biological vision, operating at wavelengths and frequencies far removed from what our eyes can detect. This was a profound conceptual leap, opening up an entirely new universe of unseen phenomena. As the visionary poet William Blake so evocatively and profoundly wrote in his enduring work, The Marriage of Heaven and Hell, if the doors of perception were cleansed, everything would appear to man as it is, infinite, for man has closed himself up till he sees all things through narrow chinks of his cavern. Indeed, this poetic insight holds a deep scientific truth. We, as human beings, experience only a vanishingly small portion of the vast, boundless spectrum of what light, in its broadest electromagnetic sense, has to offer. The physical reality of light is, in truth, a doubly infinite space, a multidimensional continuum of information, from which we can only perceive a highly limited three-dimensional projection. Do not be intimidated or alarmed by this seemingly complex or abstract statement. Its profound meaning and implications will soon become strikingly clear as we delve deeper into this exploration, revealing the hidden dimensions of our sensory world. Consider a historical photograph of a young James Clerk Maxwell. What is particularly engaging and profoundly insightful in this image is not merely his thoughtful, perhaps even somewhat intense gaze, the kind of contemplative look that might, to a casual observer, suggest a personality that is a touch peculiar or exceptionally focused, a mind constantly at work, but rather the fascinating and seemingly innocuous device he holds gently in his hand, a colour top. Of course, the photograph itself is, by its very nature, monochromatic, captured in shades of grey, a limitation of the photographic technology of the era. Colour photography, as a practical and widespread technology, had not yet been invented. Maxwell himself, with his pioneering work on colour and his deep understanding of light, would in fact later create the world's first durable colour photograph in 1861, a testament to his comprehensive theoretical and practical grasp of the subject. This seemingly simple toy, this unassuming colour top, was meticulously designed and purposefully constructed by Maxwell for the express scientific purpose of rigorously investigating and systematically studying the intricate mechanisms of human colour perception. It represents a profound idea, deceptively simple in its physical execution, yet profoundly insightful in its intellectual implications, transforming what might appear to be a mere child's plaything into a powerful, sophisticated instrument for groundbreaking scientific discovery and a deeper understanding of our own subjective sensory experience. What precisely was the essence of this profound idea, and how did the colour top work? In a previous shorter exploration of the hypothetical nature of extraterrestrial civilizations, I briefly touched upon the intriguing and often counterintuitive nature of two distinct types of yellow. One can obtain a pure or spectral yellow, a yellow of a single specific wavelength, by passing a beam of white sunlight through a prism, which, through the phenomenon of dispersion, separates the light into its constituent colours, much like a natural rainbow. This is the yellow that exists as a distinct band in the electromagnetic spectrum. However, one can also achieve the sensation of yellow by simply additively mixing specific proportions of spectral red and spectral green light. Physically, these two yellows are profoundly and fundamentally different entities. The spectral yellow is a coherent wave of a single, specific wavelength, an electromagnetic oscillation at a precise frequency. In contrast, the mixed yellow is a combination of two distinct separate wavelengths, two different frequencies of electromagnetic radiation, striking the eye simultaneously. Yet, to our human perception, to our subjective experience, both appear absolutely identical. This remarkable phenomenon, where physically distinct stimuli produce the very same perceived colour, is a cornerstone of colour science and is known as metamerism. It vividly illustrates the interpretative, rather than purely objective, nature of our colour vision. Our brain receives different physical inputs but constructs the same internal experience. Similarly, it is not necessary, nor is it physically required, to combine all the diverse colours of the solar spectrum, the entire visible rainbow, to produce white light that appears indistinguishable from natural sunlight. Instead, one can simply mix precise proportions of red, green, and blue light to achieve a white that is, to the human eye, absolutely identical in its perceived hue and brightness to the full continuous spectrum of sunlight. And again, as a physical entity, this additively mixed white light, composed of just 3 primary wavelengths, is significantly and fundamentally different from the continuous, full spectrum of sunlight, which contains all visible wavelengths in a smooth distribution. Yet, human vision, with its inherent biological processing limitations, perceives both as being exactly the same, a perfect match. This concept, the creation of white from just 3 distinct colours, is remarkably counterintuitive, especially when contrasted with our everyday experience of mixing paints. The very idea of combining blue, red, and green light to suddenly produce the purest, most brilliant white seems almost magical, defying common sense if one is accustomed only to the subtractive processes of mixing pigments. This distinction highlights precisely why one can never achieve anything remotely similar with physical paints or pigments. When you engage in the act of painting, you are, in essence, selecting which spectral colours your chosen surface absorbs and which it reflects. Pigments work by subtracting certain wavelengths from the incident light. If you mix a sufficient quantity of various different pigments, that is, if you combine materials that are designed to each absorb different parts of the visible spectrum, you will ultimately create a surface that is capable of absorbing almost all incident light across the entire visible spectrum. The inevitable result of this extensive absorption is an absence of reflected light, which we then subjectively perceive as black. The process of adding light, known as additive colour mixing, which is what happens with the colour top and on-screens, is fundamentally simpler and, from a physical perspective, more basic and foundational than the subtractive process of mixing pigments. Pigments work by subtracting, absorbing certain wavelengths from the light that hits them, reflecting the rest. When you mix more pigments, you subtract more wavelengths, eventually leading to a dark, muddy brown or black. Light mixing, however, adds wavelengths together, and adding red, green and blue light leads to white. The crux of the matter, the central scientific puzzle that Maxwell sought to unravel with his colour tops, is that physically distinct combinations of spectral colours can, and often do, appear identical to our sophisticated yet limited visual system. The critical scientific challenge, then, was to systematically and rigorously identify precisely which specific combinations of light produce these identical perceptions and, crucially, to understand the fundamental nature of the space to which these subjectively perceived colours truly belong. It was for the meticulous and rigorous investigation of these very questions that Maxwell ingeniously conceived and developed his now famous colour tops. Take a moment, if you will, to momentarily set aside the vast accumulation of knowledge from the 21st century and allow yourself to genuinely marvel at the elegant simplicity and the profound intellectual insight embodied in their operation. These tops were essentially discs divided into coloured segments that could be spun rapidly. For the vast majority of human history, stretching back through countless generations, people largely assumed, as a matter of intuitive common sense, that vision provided us with an instantaneous, perfectly accurate, continuous, and utterly faithful snapshot of reality. It was believed to be a perpetually flowing, unmediated reflection of events, unfolding seamlessly in time, a direct, transparent window onto the objective world, with no filters or interpretations. However, our vision is, in a far more accurate and scientifically informed sense, merely a highly sophisticated sequence of discrete, momentary snapshots, individual frames, each captured with an effective exposure time of approximately 1/25th of a second. This means, quite literally, that our visual system is effectively receiving a somewhat modest, and perhaps even underwhelming 25 individual frames of visual information per second. This is far from a continuous stream, but here, a truly remarkable and almost magical form of neurological processing intervenes. Our brain actively and continuously fills in the temporal gaps, the imperceptible intervals, between these individual momentary snapshots, meticulously constructing the seamless flowing illusion of continuous motion. This extraordinary feat of neural computation, known as persistence of vision, allows us to perceive a smooth, uninterrupted world. This is precisely why, on occasion, when one gazes intently at the second hand of an analog clock, it might momentarily appear to freeze, to stick, for a fraction longer than usual before jumping to its next position, a subtle yet fascinating trick of our temporal perception, as the brain struggles to smooth out the discrete movements. The most widely recognized and commercially successful application of this peculiar and exploitable characteristic of our human vision is, of course, the art and technology of cinema, where a rapid succession of still images creates the fluid illusion of movement. Maxwell's color top operates on precisely this same fundamental principle, cleverly exploiting the inherent inertia or persistence of our vision. As the color top spins rapidly, its various colored segments blurring into one, our eyes effectively integrate or additively combine the reflected light rays from these rapidly changing colored areas. If the top has segments of red, green and blue at a certain speed, the eye perceives them as blended into white. The color tops, as meticulously designed and constructed by Maxwell, allowed for a systematic, quantitative and incredibly precise determination of which specific combinations of colors, when rapidly presented, appear identical to the human observer. He could vary the proportions of each color on the spinning disc. The most significant and groundbreaking finding derived from these pioneering investigations was the profound revelation that by utilizing just 3 fundamental colors, specifically red, green, and blue light, it is possible to match or perceptually recreate any other color within the human visual spectrum. For example, by precisely mixing spectral red, green, and blue light in varying carefully controlled proportions, we can generate the subjective perception of orange, yellowish green, reddish brown, sky blue, deep magenta, or indeed any other desired hue or shade. This trichromatic theory of color vision, first proposed by Thomas Young and later refined by Helmholtz and Maxwell, became the bedrock of modern color science. This fundamental principle, elucidated by Maxwell's rigorous experiments and theoretical work, is, in fact, what underlies the entire visual experience you are having at this very moment. The screen upon which you are currently experiencing this monologue, whether it be a computer monitor, a tablet, or a smartphone, does not, in truth, reproduce the full, continuous spectrum of all possible colors. Instead, it generates all its perceived colors by varying the relative intensity of only 3 fundamental light sources: tiny red, green, and blue subpixels. These are the primary colors of additive light. When display manufacturers promise millions of colors on a screen, they are not referring to physically distinct spectral wavelengths for each color. Rather, they are referring to the millions of distinct and unique ways in which the relative intensities of these 3 primary light sources can be combined and adjusted to create a vast gamut of perceived colors. The human eye and brain then blend these 3 light sources into the full spectrum of hues. In essence, this means we can precisely define and communicate any perceived color by simply specifying the exact amounts or relative intensities of red, green and blue light required to produce that specific hue. This system is entirely analogous to how we can precisely pinpoint a specific location in physical, 3-dimensional space by stating its exact distance from us along the cardinal axes of north-south, east-west and vertical elevation. Just as ordinary physical space is a 3-dimensional continuum defined by 3 coordinates, x, y, and z, so too is the complex and nuanced space of perceived colors a 3-dimensional continuum, a concept known as a color space, where each color can be represented as a point with 3 coordinates, r, g, b. Consider, as another compelling example, an artwork, perhaps one of Claude Monet's iconic Haystacks series, or any of the masterpieces of Impressionist painting. These paintings can be appreciated as another, albeit spatially oriented form of Maxwell's color top, one that harnesses the inherent persistence of vision not through rapid changes over time, as with the spinning top, but through the spatial integration of discrete elements. The individual brush strokes, when viewed from a distance, blend together. For artists, the profound artistic and creative liberation that comes from the ability to achieve the exact same perceived color through a multitude of different physical combinations of pigments, unlocks a vast and rich realm of creative possibilities. It allows for the subtle addition of local texture, vibrancy, and optical mixing effects, where colours are mixed in the eye rather than on the palette, while simultaneously maintaining the overall desired averaged colour perception when viewed from a distance. Spatial averaging in this artistic context is a more nuanced, subtle, and less abrupt phenomenon than temporal averaging, thereby offering a broader and more diverse palette of artistic options and expressive techniques. By applying different pigments separately, in very close proximity to one another on various parts of the canvas, for instance, using individual dabs or strokes of pure unmixed colour, a technique known as broken colour or pointillism, rather than physically mixing them on a palette and then applying the pre-blended mixture, the Impressionist painters employed a sophisticated visual strategy, remarkably similar in principle to that utilised in Maxwell's colour tops, but transposed from the temporal domain of rapid spinning into the spatial domain of juxtaposed brushstrokes. In both instances, whether it's the spinning top or the painted canvas, light originating from distinct sources or different areas is combined and integrated by the eye and brain according to the rules of additive light mixing, because the artist, in essence, is mixing not the paints themselves on the canvas, which would be subtractive, but rather the light reflected from them that travels to and reaches the observer's eye, which is an additive process. But what fundamentally and at its very core is the light that we perceive? What is its true underlying nature beyond its perceived colours and its role in vision? The light that is visible to human eyes is, in scientific terms, a very specific and narrow manifestation of a much broader phenomenon, an electromagnetic wave. It exists within a remarkably confined range of wavelengths, typically spanning approximately 370 to 740 nanometers, a tiny band within a vast spectrum. If this information is new to you, prepare for a truly astonishing and profoundly beautiful revelation, because the electromagnetic wave itself possesses an exquisitely mesmerizing and elegant structure. Imagine, if you will, a perfect self-propagating wave, an electric field oscillating, vibrating rhythmically in a particular plane, for instance, vertically moving up and down. Perpendicular to this oscillating electric field, at a precise 90-degree angle and oscillating in perfect synchronized harmony, is a magnetic field, perhaps oscillating horizontally, moving side to side. Crucially, both of these fields, the electric and the magnetic, are in turn oscillating perpendicular to the direction in which the wave itself is travelling through space, a third axis of perpendicularity. This intricate arrangement forms an exquisitely perfect three-dimensional construction, a dynamic dance of perpendicularity, a precise and elegant geometry that Maxwell, with astonishing clarity and foresight, described mathematically and verbally in his groundbreaking formulations. This is a structure of pure dynamic symmetry, but the wonder of this phenomenon does not conclude there. In fact, it only deepens, revealing the self-sustaining nature of light. This is a truly self-sustaining and self-propagating process, a cosmic feedback loop. Changes or oscillations in the electric fields inherently induce corresponding changes or oscillations in the magnetic fields. These induced changes in the magnetic fields, in turn, generate electric fields, and this intricate reciprocal dance of mutual creation and regeneration continues, propagating through the vastness of space at an incredible speed, seemingly unto infinity. The first field, in essence, continually gives birth to the second, which in turn gives birth to the first, creating an endless, rhythmic propagation without requiring a medium. This fundamental principle is the very essence of how light, and indeed all forms of electromagnetic radiation, travels through the cosmos, from the heart of a star to the retina of your eye. It was James Clerk Maxwell who, with unparalleled intellectual brilliance, unified electricity and magnetism, recognizing them not as separate and distinct forces, as they had been treated for centuries, but as two inseparable facets of a single, overarching, and fundamental force, the electromagnetic force. In doing so, he not only revealed the profound possibility of the existence of self-propagating electromagnetic waves, but crucially, he precisely calculated their speed through a vacuum. Maxwell's astonishing discovery was that this calculated speed precisely matched the previously measured speed of light, which had been determined through independent experimental observations by figures like Römer and Fizeau. For Maxwell, this remarkable coincidence was irrefutable, undeniable evidence. A profound revelation that light itself is in fact entirely composed of these very electromagnetic waves, possessing this captivating self-renewing geometry and an inherently self-sustaining nature of existence. So if you ever find yourself contemplating something that appears less than beautiful, or perhaps even mundane, if you gaze at a seemingly plain wall or a simple object, you can always recall the magnificent, elegant and profoundly beautiful underlying structure from which that observed scene, that perceived image, is composed, a symphony of oscillating fields moving through space. To this very day, this remains our most fundamental, comprehensive and accurate scientific description of light and its propagation. Visible light, however, despite its profound importance to our perception and its central role in our experience of the world, corresponds to only a minuscule sliver, a very narrow band, of the entire electromagnetic spectrum. This vast, continuous spectrum, stretching far beyond what our eyes can detect, includes electromagnetic waves of every conceivable wavelength, from the longest radio waves, which can span many kilometers and are used for communication, to the shortest gamma rays, with wavelengths smaller than an atomic nucleus and possessing immense energy. We now understand, thanks to Maxwell's initial predictions and subsequent experimental confirmations, that not only visible light, but also radio waves, which carry our broadcasts and wireless communications, microwaves, used in ovens and radar systems, infrared radiation, which we perceive as heat and is used in night vision, ultraviolet radiation, responsible for sunburns and vitamin D production, X-rays, used in medical imaging to peer inside the body, and gamma rays, emitted during radioactive decay and cosmic events. All of these are fundamentally manifestations of the same phenomenon, electromagnetic waves. They differ only in their wavelengths, their corresponding frequencies, and their energy levels, forming a continuous spectrum of existence. And it was Maxwell who, with astonishing intellectual prescience and mathematical rigour, first predicted their existence and laid the theoretical groundwork for their understanding, unifying seemingly disparate phenomena into a single grand theory. Consequently, if you consider the myriad benefits and astonishing technological advancements of modern civilization, from the instantaneous global communication enabled by radio and microwaves, to the life-saving capabilities of X-ray imaging, to the ubiquitous data transmission that underpins our digital age, as truly advantageous and transformative, then your gratitude should, in large and perhaps even primary measure, be directed towards the unparalleled genius and profound insights of James Clerk Maxwell. He truly laid the conceptual and mathematical foundations for so much of what we now take for granted, ushering in the age of telecommunications and modern physics. Returning to the overarching concept of electromagnetic waves, it becomes strikingly clear, upon deeper examination, that a colossal, indeed almost unfathomable, portion of this vast spectrum simply and completely escapes the direct apprehension of our biological vision. Our eyes are tuned to a very specific narrow band, like a radio receiver fixed on a single station, while millions of others broadcast simultaneously. We are, by our very nature, compelled to rely on a diverse array of specialized sensors, intricate instruments, and sophisticated detectors to register and interpret this boundless, turbulent, and profoundly rich ocean of electromagnetic energy in which we are constantly immersed. This ocean, teeming with information and forces, remains entirely beyond the grasp of our innate unassisted senses. For instance, we cannot directly perceive radio waves. They pass through us, through our homes and across continents, carrying complex information, yet remain utterly invisible, intangible, and unheard. Without the ingenious invention of radio receivers and transmitters, the fundamental technologies of wireless communication, we would to this very day remain completely oblivious to their constant presence and the vast amounts of information they carry, much like fish unaware of the water they swim in. Yet, even when we restrict our discussion solely to visible light, that narrow familiar band of the spectrum that our species has evolved to perceive over millions of years, precisely because our planet's atmosphere most efficiently transmits these particular wavelengths, making them ecologically relevant, our perception still does not grant us the capability to fully and completely utilize even this relatively meager resource. Our biological filters, our sensory limitations, prevent us from grasping its full complexity and extracting all the information it carries. Ask yourself then, what are the precise constituent parts, the fundamental components of the signal that continuously streams into your eyes, forming the basis of your visual experience? The answer, upon careful analysis and neuroscientific understanding, reveals that there are, in essence, two primary and distinct components. The first is the spatial signal. This component carries crucial information about the direction of light rays originating from various points and objects in our environment. It is this information that allows us to form the contours, the outlines, the shapes, and the overall configuration of the images we perceive, enabling us to spatially organize our world to understand depth, form, and movement. This creates the what and where of vision. The second primary component is the chromatic or color aspect, and it is precisely here that the truly interesting, complex, and often counterintuitive details begin to unfold, pushing us beyond simple spatial mapping. This signal contains information of a fundamentally different nature. We are capable of perceiving images in stark yet informative black and white, a world of shades of grey like an old photograph, which relies solely on intensity differences. Or we can experience them as vibrant, rich and full-colour representations, a world bursting with hues and saturation, adding another layer of descriptive power. In certain extreme cases, such as an overwhelming flash of intense light, or prolonged staring at a bright source, we might simply perceive solid, undifferentiated fields of intense colour that momentarily overwhelm and saturate our eyes, preventing the formation of distinct images, a blinding wash of pure hue. If we have, in broad strokes and general terms, come to a basic understanding of what light is in its entirety, an electromagnetic wave, then what precisely is colour? What is this subjective experience that adds so much richness to our world? Frank Wilczek, with his characteristic intellectual depth and keen philosophical insight, writes that this is a profoundly deep, intricate, and indeed a truly beautiful question, far more complex than it first appears. And everything that has been discussed and elucidated thus far, every detail about sensory perception and Maxwell's equations, has served merely as a preparation, a necessary preamble, to begin to truly answer it. If we were to provide a concise yet powerful answer, it would be this. While the spatial aspect of an image contains information about what is physically occurring in space, where objects are, their shapes, their relative positions, colour, in a fascinating contrast, tells us about what is happening in time, specifically regarding the temporal frequency of the electromagnetic waves themselves. It's a measure of the wave's rhythm. For example, when we subjectively perceive a pure, unadulterated spectral yellow, our eyes, through their intricate biological mechanisms and neural processing, are, in essence, communicating to our brain that the incoming electromagnetic waves are pure, perfectly sinusoidal waves that repeat themselves at an astonishingly high rate, approximately 523 trillion times per second. This incredibly rapid oscillation is what our brain interprets as yellow. When we perceive a pure spectral red, the message conveyed to the brain is that these repetitions, these oscillations, are occurring at a different yet equally precise frequency of approximately 450 trillion times per second. This incredibly rapid, yet distinct, vibrational rate is what we experience as red. This sounds, on the face of it, incredibly precise, profoundly insightful, and almost impossibly cool in its implications, linking our subjective experience directly to fundamental physical properties of light. However, there is a crucial, indeed central caveat, a profound but. which lies at the very heart of the problem of these lost infinities, these dimensions of reality that remain entirely unseen and unperceived by us. The fundamental issue, the core limitation of our biological vision, is that our eyes, despite their sophistication and sensitivity, do not differentiate between physically distinct stimuli that produce the same perceived colour. This is the phenomenon of metamerism at work, and it's a profound bottleneck. They do not, for instance, distinguish any physical difference between a pure spectral yellow, which is a single specific wavelength of light, and a yellow sensation created by the additive mixture of red and green light, which involves two distinct wavelengths arriving at the retina simultaneously. Both physical inputs lead to the same internal sensation of yellow. Similarly, they do not perceive the physical difference between a pure spectral red, a specific wavelength, and the vast multitude of other colour combinations, various mixtures of other wavelengths and intensities, that also perceptually appear red to us. In essence, an enormous number of distinct and physically unique input signals are all grouped together, categorised, and funneled into a single, overarching perceptual category, or, more accurately, into three such categories, corresponding to our three primary colour sensations. Our visual system acts as a powerful data compressor, sacrificing information for efficiency. Wilczek articulates this limitation with striking clarity and scientific precision. A true analysis of the input signal, in the aspect of colour, ought to extract the same information as Newton's analysis of light, by means of a prism. In other words, such an ideal, complete and uncompromised analysis would meticulously and precisely decompose the incoming light signal into all of its pure spectral components, revealing the exact intensity of every single wavelength present, much like a prism separates white light into a rainbow. Each of these pure spectral components possesses its own independent intensity. To fully and accurately represent the result of such a comprehensive analysis, we would require a continuous, indeed an infinitely long sequence of numbers, one number for the contribution, the intensity, of each pure spectral component across the entire continuous spectrum of wavelengths. This conceptual space of potential information, this boundless data carried by light, is not merely infinite in its extent. It possesses an infinite number of dimensions, one for each possible wavelength. Yet, the projection of this vast, infinitely dimensional information that our eyes actually perceive, as Maxwell so brilliantly uncovered through his experiments with colour matching, consists of only three discrete numbers. This concept might indeed sound complex and abstract, and I myself have revisited these explanations numerous times to truly grasp their full, profound implication. But, to put it succinctly, the space of objective, physical colour information is infinitely dimensional, a boundless continuum of possibilities, describing every single photon's wavelength and intensity. However, what we subjectively perceive as colour is merely a three-dimensional surface, a highly limited projection, onto which these infinite dimensions of physical colour information are compressed, simplified, and filtered. Thus, an entire infinity of information, a vast realm of hidden data, continuously eludes our direct gaze and conscious perception, forever remaining beyond the reach of our natural vision. But, as Frank Wilczek further reveals, with a depth that is both intellectually exhilarating and perhaps a little unsettling in its implications for our understanding of reality, the reality of our sensory limitations is, in fact, even more profound and, in a sense, even worse than this initial revelation. This infinity of information, strictly speaking, is not merely infinite, it is doubly infinite. The amount of information we miss is not just immense, but compounded. Why is this the case? The answer lies in a fundamental and often overlooked property of light known as polarization. Let us once again visualize in our minds the intricate structure of an electromagnetic wave, as Maxwell described it. We can imagine the electric fields oscillating, vibrating rhythmically, in a particular plane, for instance vertically, moving up and down in relation to the direction of travel. Perpendicular to this oscillating electric field, at a precise 90-degree angle, and oscillating in perfect synchronized harmony, is a magnetic field, perhaps oscillating horizontally, moving side to side. This is one possible configuration. However, there exists a second, equally valid and precisely opposite configuration. One where the electric fields oscillate horizontally and the magnetic fields oscillate vertically. This rotated or orthogonal solution oscillates at precisely the same temporal frequency as the original wave, meaning it objectively represents the exact same spectral color and carries the same energy. Yet, physically and fundamentally, it is entirely distinct in its orientation of oscillation. This specific property, this spatial orientation of the electric field's oscillation, is what we refer to as the polarization of the wave. Light can be polarized in many different ways: linearly, horizontal, vertical, or at an angle, circularly or elliptically. The phenomenon of polarization is not merely an abstract concept confined to physics laboratories. It has tangible, everyday applications that we might not even consciously recognize, subtly shaping our visual experience. You can easily observe and understand polarization by considering a common example: polarized sunglasses. These specialized lenses are meticulously designed to transmit light, or electromagnetic waves, that vibrate only in a single specific plane, effectively blocking out light that is oscillating in other planes. By doing so, they significantly reduce glare, often caused by light reflecting off horizontal surfaces like water, snow, or roads, which tends to become horizontally polarized. This selective filtering minimizes the strain on our eyes, enhances visual comfort and clarity, and allows us to sense objects more sharply by removing the scattered, depolarized light. Consequently, the electromagnetic information entering our eyes at every single point within an image, at every perceived pixel of our subjective reality, possesses an infinite number of dimensions, and this is true twice over. This doubling occurs because for every single spectral color, each distinct wavelength of light, there exist two possible independent polarization states, e.g., horizontal and vertical linear polarization, or right and left circular polarization, and each of these states can vary in its strength or intensity independently of the other. Our human vision, however, remains utterly oblivious to this fundamental doubling, this rich, additional layer of information encoded in the light. The human eye simply does not register any difference between light of various polarizations. Our photoreceptors are generally insensitive to the orientation of the electric field. As we have come to understand through this extended exploration, our visual system, while extraordinary, misses quite a lot of the objective physical reality of light, simplifying it for our practical needs. A more beautiful, precise, and philosophically resonant way to articulate this profound limitation is to state that our perception of colour projects the doubly infinite dimensional space of physical colour, which includes both spectral composition and polarization, onto the humble, restricted three-dimensional wall of our internal subjective cave of consciousness. To truly escape the confines of this cave, to truly apprehend these additional hidden dimensions of light, we must embark on a journey of scientific discovery, utilizing tools and instruments that extend and augment our natural biological capabilities, allowing us to perceive beyond our inherent limitations and glimpse the richer, more complex reality that surrounds us. But one might reasonably and logically inquire, what are the specific biological underpinnings, the evolutionary and physiological reasons for this particular characteristic and inherent limitation of our vision? Why have we evolved to perceive only three dimensions of colour and no polarization? The answer lies deep within the intricate molecular architecture of our photoreceptor cells. Information about colour is primarily extracted and processed by three distinct types of protein molecules known as opsins, which are housed within the specialized cone cells of our retina. These cones are concentrated in the fovea, responsible for high acuity color vision in brighter light. When a photon of light, a single packet of light energy, encounters one of these opsin molecules, there is a specific measurable probability that the molecule will absorb this unit of light. Upon absorbing the photon, the opsin molecule undergoes a rapid and precise change in its molecular configuration, a conformational shift like a key turning in a lock. This change in shape in turn triggers a minute yet critical electrical impulse, a signal that is the fundamental unit of information our brain then utilizes through complex neural pathways to construct our subjective sense of vision. This is the process of phototransduction, converting light into a neural code. Crucially, the probability that an individual unit of light, a single photon, will be absorbed by a given opsin molecule depends both on its spectral colour, its specific wavelength or energy, and on the unique chemical and structural properties of the receptor molecule itself. Each opsin type is sensitive to a different range of wavelengths. One type of receptor, for instance, is more inclined, or tuned, to absorb light from the red portion of the spectrum, exhibiting its peak sensitivity in that range. This is often called the L-cone, long wavelength sensitive. Another type reaches its peak form, or maximal absorption, in the green region of the spectrum known as the M-cone, medium wavelength sensitive. While a third type is most sensitive to blue light, the S-cone, short wavelength sensitive. It is important to note that the tuning of these receptors is not narrowly confined. Each type responds across a broad range of wavelengths, with significant overlaps in their absorption curves. The brain then compares the signals from these three types of cones to create the sensation of colour. Thus, the profound insights of physics, and Maxwell's work in particular, provided biologists with a clear and indispensable roadmap, guiding them precisely what to look for and how to investigate the extraordinarily complex and vitally important organs designed for vision. The task, in essence, became one of simply counting the number of distinct receptor types and meticulously measuring their precise light absorption capabilities, a perfect example of interdisciplinary scientific advancement. This interdisciplinary synergy between physics and biology unlocked a deeper, more mechanistic understanding of the fundamental mechanisms underlying colour perception. Consider, as a vivid and often cited illustration of this principle, the classic image of a bullfighter's vibrant red cape. Is the cape's colour truly for the bull? Does the bull perceive its fiery hue? Of course not. Its striking redness, its dramatic visual impact, is entirely for the benefit and dramatic engagement of the human spectators, who respond emotionally to the colour. Bulls, it turns out, perceive the world primarily, if not exclusively, in shades of grey, essentially experiencing a monochromatic reality, similar to a black and white film. Their visual systems lack the necessary cone cells, or at least lack the diversity of cone cells, to discriminate between different hues. They react to the movement of the cape, its flapping and swirling, not its colour. Dogs, while possessing a somewhat more advanced visual system than bulls, still experience what is known as dichromatic vision, meaning they perceive a two-dimensional space of colours, typically sensing the world in shades of blue, yellow and grey, but are unable to distinguish between red and green. Their world lacks the vibrant reds and greens that are so prominent in ours. Similarly, human beings who suffer from various forms of colour blindness, or daltonism, are also primarily capable of perceiving only a two-dimensional space of perceived colours, or sometimes even a one-dimensional space in rare cases of complete colour blindness. This condition typically arises from the absence of one of the three types of opsin protein receptors in their cone cells, or from the presence of mutated opsin proteins that are poorly able to differentiate between specific colours, leading to confusion between certain hues. For instance, the acclaimed filmmaker Christopher Nolan is known to be colourblind, reportedly having difficulty distinguishing between certain shades of green and red, which undoubtedly impacts his artistic choices in cinematography and his perception of the world he films. Colour blindness, particularly the common red-green type, is significantly less common in women, but it is a relatively widespread condition among men, affecting approximately 1 in 12 men in Northern Europe, owing to its X-linked genetic inheritance pattern, making it more prevalent in males. However, this raises a fascinating and counterintuitive question, one that flips our understanding of visual limitations on its head. Are there conversely individuals who possess the opposite of colour blindness, a profoundly heightened sense of colour perception, an expanded visual faculty that goes beyond the norm? The answer is a resounding yes. These exceptional individuals are known as tetrachromats. Unlike the typical human, who possesses 3 types of cone cells, they possess not 3, but 4 distinct types of colour receptors in their retinas. This unique genetic characteristic, stemming from an extra gene for an opsin protein on the X chromosome, is found in approximately 12% of women. Yet, For the majority of these women, the fourth type of colour receptor does not differ significantly enough in its spectral sensitivity from one of the existing three, meaning their overall colour perception remains to a large extent identical to that of most people. It's an unused potential. It is only in the exceptionally rare instance of an additional specific genetic mutation that the sensitivity curve of the fourth receptor type becomes sufficiently distinct and separated from the other three curves, creating genuinely novel colour channels. Such individuals are then truly capable of discerning additional subtle hues and variations, perceiving combinations of spectral colours that the vast majority of humanity perceives as absolutely indistinguishable, as mere metamers. In effect, they perceive light not in the familiar three dimensions of colour, but in an expanded, richer, and more detailed 4 dimensions, unlocking a hidden stratum of visual information and experiencing a world of colours we can only imagine. The subjective experience of such vision is, of course, utterly beyond our direct comprehension, as we lack the neural machinery to replicate it, but it hints at the vastness of unperceived reality and the diversity of sensory experiences possible. But when we consider the broader and immensely diverse tapestry of life on Earth, stretching from the smallest microorganisms to the largest whales, it becomes abundantly clear that mammals, as a class, generally possess a rather mediocre, even limited capacity for colour vision when compared to other animal groups. Most mammals, for example, are dichromats, sensing a world of blues, yellows and greys, lacking the full spectrum of our trichromatic vision. Many species of insects and birds, in stark contrast, are endowed with 4, and sometimes even 5 distinct types of colour receptors in their eyes, far surpassing human capabilities. These often include receptors that are highly sensitive to ultraviolet, UV, light, a spectrum entirely invisible to human eyes, which they use for navigation, foraging and communication. Some even possess the astonishing ability to detect the polarization of light, allowing them to perceive patterns in skylight that indicate direction, or to detect signals from other polarized objects. Many flowers, for instance, which we perceive in one way, are often elaborately decorated with intricate patterns and vibrant colorations that are strikingly visible only in the ultraviolet spectrum. These nectar guides, or bullseye patterns, serve as powerful hidden lures to attract their specific insect or bird pollinators, guiding them to the reproductive parts of the plant, an unseen world of floral advertising. Within the vast and intricate sensory universe of colour, these creatures unlock and experience dimensions of visual information that entirely elude our human perception, living in a world of unseen beauty and complexity that we can only infer through scientific instruments. However, the absolute record holders, the true possessors of what can only be described as supervision in the animal kingdom, are the captivating and often flamboyant stomatopods, more commonly known as mantis shrimp. These aggressive, brightly coloured crustaceans, famous for their powerful punching appendages, are truly visual titans. Depending on the specific species, these truly remarkable crustaceans can possess anywhere from an astonishing 12 to an almost incomprehensible 16 distinct colour dimensions in their vision. Just take a moment to truly ponder that magnitude. 12 to 16 dimensions of colour. Imagine a world so rich in hue and saturation that our human experience would feel like a pale, faded photograph in comparison. Their range of sensitivity extends far beyond mere colour discrimination, reaching into capabilities such as the precise deciphering of complex information about the polarization of light, meaning they can detect the orientation of light waves, whether linear, circular or elliptical, and even extending to the direct perception of infrared and ultraviolet light. The intricate structure of their compound eyes, which are often described as having a unique mid-band region containing these super-specialized photoreceptors, is a testament to millions of years of evolutionary refinement, allowing them to sample an incredibly broad spectrum of light and its properties. The profound question then arises inevitably from contemplating such extreme sensory differences. What could it possibly be like to experience the world as a mantis shrimp does? What is the subjective reality of perceiving in 16 colour dimensions and sensing polarised light? Is it merely more colour, Or is it an entirely different kind of qualitative experience? This inquiry immediately transports us back into the profound and often unanswerable realm of philosophy, specifically into the philosophy of consciousness, and to the most famous and persistently debated question in contemporary scientific discourse regarding the nature of subjective experience: what is it like to be a bat? This profound and endlessly debated topic, exploring the subjective, inner experience of other beings, highlighting the limits of our imaginative empathy, was something we previously delved into in a discussion about the nature of consciousness itself, emphasizing the inherent limits of empathy and imagination when attempting to cross fundamental species barriers. We can describe the physical inputs a bat receives, echolocation, but we cannot feel what it is like to see with sound. Similarly, we can describe the light properties a mantis shrimp perceives, but we cannot truly fathom its subjective visual world. While it is indeed technically possible to acquire and process data, for example, of the sun or distant galaxies in the X-ray, infrared, ultraviolet, and other invisible electromagnetic ranges using highly specialized technical equipment such as space telescopes, orbiting observatories, and advanced sensors, these datasets do not, in a literal sense, inherently possess any color in the way we understand it. These are not true color representations. For such scientific visualizations, specialized filters are employed to meticulously isolate the desired wavelength range, rigorously excluding all others. The resulting raw data, which is essentially a grayscale intensity map of a particular non-visible wavelength, is then, of course, artificially colored in some conventional, often arbitrary, manner by scientists and artists to render it perceptible and comprehensible to human eyes. For example, higher intensity in X-ray might be mapped to blue, lower intensity to red, simply to create a visual representation. So the question of what it is truly like to see in the infrared range, for instance, to have a direct, subjective, qualitative experience of infrared color, to feel the warmth of an object as a hue, remains far beyond the confines of our current human understanding and experience. We can measure it, we can display its data, but we cannot feel it, we cannot subjectively perceive it. Why the mantis shrimp, alone among so many creatures, evolved such an exceptional and multifaceted giftedness in color and polarization perception remains a significant and tantalizing question, one that continues to provoke deep scientific interest and extensive research. Its visual system seems almost over-engineered for its environment. One widely accepted and highly plausible hypothesis suggests that they utilize this extraordinary visual capacity for complex, subtle, and often rapid communication, exchanging secret messages with other mantis shrimp, communicating on channels that are completely undetectable by most other marine creatures, including their predators and prey. Imagine a world where your body is a constantly shifting, multi-dimensional signal generator. Wilczek, among other scientists, speculates that they employ their own bodies, which are often covered in intricate iridescent patterns that reflect polarized light in complex ways, to create breathtakingly impressive and rapidly changing color and polarization patterns. These dynamic visual displays are virtually inaccessible to our human perception, yet serve as vital signals within their own species. They use these dynamic displays to demonstrate their fitness and form to potential partners during elaborate courtship rituals, a dazzling display of genetic quality, to signal aggression and territorial claims to rivals, avoiding physical combat by a show of force, and even to camouflage themselves or warn off predators in ways that are visually complex and rapidly changing, breaking up their outline in a way only other mantis shrimp can fully appreciate. It is akin to a peacock's tail, but infinitely more sophisticated, dynamic, and multidimensional in its visual impact, extending into the realm of polarized light, a secret language of the ocean. In strong support of this compelling idea, we can observe that some species of stomatopods are, even to our limited human vision, astonishingly brightly and diversely colored, exhibiting vibrant hues and intricate patterns, and it is precisely those species that possess the most advanced and complex color vision systems that are often the most exquisitely and richly adorned, suggesting a direct correlation between their visual capabilities and their display strategies. These are truly astonishing creatures, embodying a profound biological mystery. How does the relatively small, compact brain of a crustacean manage to process, integrate, and effectively utilize such an overwhelming abundance of complex, multidimensional sensory information in real time without being overwhelmed? Recent research using advanced neuroimaging and behavioral studies suggests specialized neural structures, such as the reniform body in their brain, are key to integrating these intricate visual inputs, allowing for their remarkable behavioral complexity and sophisticated decision-making based on this rich visual data. James Clerk Maxwell's theory of electromagnetic fields, profound and elegant as it was initially, in his own time, often regarded as intellectually interesting but ultimately unconvincing by many of his contemporary physicists. It was a radical departure from existing frameworks, proposing invisible fields and self-propagating waves, concepts that were difficult for many to grasp without direct experimental evidence. It challenged the prevailing mechanical view of the universe. The most crucial and far-reaching prediction of Maxwell's theory, the astonishing idea that electric and magnetic fields could mutually give life to one another, propagating through space as self-renewing, self-sustaining waves, carrying energy and momentum, had not, at that pivotal moment, been experimentally confirmed. This vital and definitive confirmation, which would solidify Maxwell's place in history, would arrive a little later through the brilliant and meticulous experiments conducted by the German physicist Heinrich Hertz. In the late 1880s, Hertz successfully generated and detected radio waves, directly verifying Maxwell's predictions and demonstrating the existence of these invisible electromagnetic waves, proving that light was indeed just one part of a much larger spectrum. This breakthrough opened the door to wireless communication and all the technologies that followed. As a young man, still in the formative stages of his prodigious intellectual development, before he had made his most famous discoveries, Maxwell made a deeply introspective and remarkably prescient entry in his personal diary, a profound reflection that seems, in retrospect, to have uncannily foreshadowed the very trajectory and purpose of the life he was destined to live. He wrote, in words that resonate with timeless wisdom and a deep sense of purpose, "Happy is the man who in the work of today sees a consistent part of the work of his whole life and the embodiment of the work of eternity. The grounds of his confidence are not changed, therefore he divides the infinite. He works hard at his daily matters because the present is given to him as his own property. Thus, man should be an embodiment of the divine processes in nature and advance the union of the infinite with the infinite, not neglecting the temporality of his existence, remembering that in him only a single action is possible, and not ignoring from his point of view the eternal, knowing that time is a mystery, the contemplation of which man will not be able to endure until eternal truth illuminates it." These incredibly rich, densely packed, and profoundly insightful lines were penned when Maxwell was merely 23 years old, a testament to his early philosophical and scientific maturity, demonstrating a mind already grappling with the most profound questions of existence and scientific purpose. By the remarkably young age of 25, he would ascend to the prestigious position of a professor at Aberdeen College, beginning his formal academic career. By 29, he was already widely recognised as one of Great Britain's foremost and most influential physicists, his ideas beginning to shape the scientific landscape. And then, tragically, at the premature age of 48, an age when many scientists are just reaching the zenith of their careers and making their most profound contributions, he would pass away, leaving behind an intellectual legacy that continues to shape our world in countless, often unseen ways. If you ever find yourself fortunate enough to be in the historic and beautiful city of Edinburgh, Scotland, a city steeped in intellectual history and scientific advancement, I implore you not to deny yourself the profound pleasure and intellectual satisfaction of experiencing his enduring legacy firsthand. There stands a magnificent and evocative monument to Maxwell, a powerful bronze statue depicting him with a gaze that seems to pierce into the infinite, a look of deep contemplation and scientific inquiry, holding with quiet reverence a colour top in his hand. It is a potent and fitting symbol, encapsulating both his boundless genius and his profound, enduring contribution to our understanding of the universe, representing his unification of light and electromagnetism and his insights into colour vision. The monument stands as a silent yet powerful testament to a man who, through sheer intellect, unwavering curiosity, and a deep appreciation for the underlying beauty of natural laws, opened new doors of perception for all of humanity, revealing infinities that were previously hidden and forever changing our understanding of light, electromagnetism, and the very fabric of reality itself. The intricate dance of light and perception, the hidden infinities that ceaselessly surround us, constantly bombarding us with information, and the remarkable ongoing journey of scientific discovery that continues step by painstaking step to unveil them. These are the profound and interconnected threads that are woven into the very fabric of our reality. Our senses, while undeniably wondrous and capable of astonishing feats, are ultimately but limited instruments, like specialized tools, offering us a carefully curated, filtered, and often incomplete version of the boundless, multifaceted universe. They are our primary interface, but not the entirety of reality. Yet through the relentless curiosity, the profound insight, and the unwavering dedication of minds like Maxwell's, we are continuously granted ever deeper insights into the true, underlying nature of existence, pushing the boundaries of what we thought possible to know. This relentless pursuit of knowledge pushes the very boundaries of our understanding, expanding the intellectual and perceptual walls of our conceptual cave, allowing us to glimpse realities that once seemed entirely unimaginable, revealing the universe to be far richer and stranger than we could have ever conceived. The inherent beauty of physics, the elegant simplicity and profound power of its fundamental laws, and the persistent, insatiable human quest to comprehend the cosmos continue, without end, to inspire awe, wonder, and a profound sense of intellectual comfort, gently guiding us into a state of quiet contemplation. These are the thoughts that can accompany you as you drift into the deep embrace of slumber, knowing that the universe, in its infinite complexity and beauty, holds endless wonders, both seen and unseen, waiting to be discovered even in the quiet moments before sleep.